Right, in this second video I'm going to go through the answers to the written questions in the past paper homework. So, the first couple of questions were from the 2019 past paper. Question 2 said, 2019 is the 150th anniversary of the periodic table's creation by Dmitry Mendeleev. The patterns identified by Mendeleev form the basis of the modern periodic table. The major periodic trends include ionization energy and covalent radius. I've just underlined these phrases because, again, if you were doing these as part of a bigger past paper, once you've studied about, however many topics there are in higher chemistry, these are clues that tell you that this question is related to this topic, periodicity. So you've got part A showing you the first ionization energies of elements with atomic number 1 to 20 are shown in the graph. You've got your graph here, and part 1 says, explain why the first ionization energy shows an increase going from lithium to neon. Now, before I go over that specific question, I want to look at a couple of things. So, when you're answering questions on ionization energy, covalent radius, or also electronegativity, there's some key phrases that I want you to try and get into your answer, and the reason for that is that that's what tends to come up in the marking scheme. So if you're talking about elements in the same period, the key phrase you tend to want to get in is nuclear charge, because we've got to remember as we go across a period, the key thing that's happening is we have an increased number of protons in the nucleus, and therefore an increasing nuclear charge. Some of you have got a little bit mixed up here, and you've also mentioned the fact that we've got an increasing number of electrons as we go across a period. That's true, and the increasing number of electrons, there is some link between the stability of the electron configuration and things like the ionization energy. So that is relevant, and that the stability of the electron configuration explains some of these little dips, but we won't go into that level of detail until we do advance higher. Because the electrons, whilst there are an increasing number of electrons as we go across a period, because the electrons are being added to the same energy level, that doesn't really affect these properties, ionization energy, covalent radius, or electronegativity very much. As we go across the period, the key thing that you want to think about is the effect of increasing nuclear charge. And as we increase nuclear charge, the outer electrons, no matter how many of them there are, there's increasing numbers as we go across a period, but because they're in the same outer energy level, they're going to get more strongly attracted to the nucleus as we go across the period because of increasing nuclear charge. If you are looking, however, at elements in the same group, or indeed if you're looking at electrons in different energy levels, I should just put that in there. So if you're looking at elements in the same group or electrons in different energy levels, then what you want to refer to is the number of energy levels, and that relates to this thing called the shielding effect. And once you've thought about which one of these you're talking about, you can then also link it to the strength of attraction between the electrons and the nucleus. What you want to be sure that you be clear about is which electrons you're talking about. So if you're talking about the outer electrons, or whether you're talking about electrons in a particular shell. So question 1 was about explaining the first ionization energy, why it shows an increase going from lithium to neon. You should recognise that that's going across a period, and so the key phrase you're going to use is, as we go across from lithium to neon, elements have an increasing nuclear charge, so the outer electrons are more strongly attracted to the nucleus. So we've gone from elements in the same period, nuclear charge, so they're more strong, the outer electrons are more strongly attracted to the nucleus. You could actually a lot of you have answered this question by just saying that neon has a higher nuclear charge than lithium, rather than talking about it in terms of a trend. That's absolutely fine. And what you can see in the answer scheme is that you get a mark just for mentioning increasing nuclear charge or increasing number of protons. You must mention either of these phrases, nuclear charge or number of protons. Nobody, I think, said nuclear pool, but that phrase is too vague. You need to mention the nuclear charge or the number of protons. And you mustn't get confused and think that it's to do with electrons being somehow having magically more attraction for the nucleus. It's to do with increasing nuclear charge, and that's what leads to the stronger attraction between the electrons and the nucleus. I hope that makes sense. Our next question then, it says explain why the first ionization energy of potassium is less than the first ionization of lithium. Ionization energy of lithium. This one was very well answered, and in general I think so. Potassium and lithium, we can see them here and here on the graph. We're looking at elements in the same group, so we need to talk about number of energy levels and shielding effect, and relate that to the strength of attraction between the outer electrons and the nucleus. Mostly that was very well answered, so most of you said something like potassium is further down the group, so has more energy levels or electron shells, meaning there is increased shielding of the outer electrons from nuclear charge, and they are less strongly attracted to the nucleus. You would get a mark if you just said increased shielding. You would also get a mark if you linked this to the fact that as we go down the group, covalent radius increases, so attraction of the nucleus for the outer electrons decreases. And some of you were very thorough and you mentioned both of these things, so that's absolutely perfect. Right, this next one here, this is a more difficult question, I think. So we've got a graph showing the ionization energies from nitrogen. For nitrogen, remember we've got these are the successive ionization energies, so we're imagining, I've got a wee diagram of a nitrogen atom here. Each time we remove an electron, that's the next ionization energy. So the first one is removing the first electron, then another, then another, then another, and so on. The first question, part I, is just write the equation for the second ionization energy of nitrogen. Mostly that was very well done. The key thing to remember here is to fill in your state symbols. A couple of you made some silly mistakes, like forgetting to add in the electron in this equation. So just remember, that'll just take a little bit more practice. But most of you were absolutely right on this. And then the second question is explain fully the increase between the 5th and 6th ionization energy of nitrogen. And that was a 2-mark question. Hopefully, if I make that a wee bit smaller, you can see that that's a 2-mark question there. So, most of you, again, this was mostly really well answered. Most of you have noticed that the 5th ionization energy, so this one here, involves removing the last of these electrons from the outer energy level of nitrogen, or the outer electron shell, whereas the 6th involves removing an electron from the inner shell. A lot of you have just lost marks to do with the way that this question is marked. So you get 1 mark just for recognising that the 6th ionization energy involves removing an electron from a shell which is an inner shell or a more stable shell, or a shell that's closer to the nucleus. For the second mark, you have to mention one of 2 things, and this is where I'll go back to the key phrases. Okay, so for the second mark in that question, you have to either mention shielding effect, or you have to mention the strength of attraction between the electrons and the nucleus. So how that relates to the question here is that you would need to say that as well as the 5th ionization energy is removing the last electron from the outer shell, whereas the 6th ionization energy is removing an electron from the inner shell, or something along those lines, you would also need to say the 6th electron is more strongly attracted to the nucleus, as there is a lower shielding effect and it is closer to the nucleus. So if you just said lower shielding effect on its own, that would be enough for the second mark. Or if you said the 6th electron is more strongly attracted to the nucleus, that would again be enough for that second mark. So it's just to do with the way that that's marked here. So you're getting 1 mark for either this point or this point, and then 1 mark for either saying that the 6th electron is less shielded or not shielded because there's no inner shells, or that the 6th electron is more strongly attracted to the nucleus. Okay, I hope that makes sense. The final one that we're going to look at then is this one here. Now, this one was a little bit sneaky of me putting this in because this is to do with this topic, but we'll go into this in a lot more detail, or we'll do a lot more practice of this in topic 2. But it is about structure and bonding. It's about structure and bonding in the first 20 elements, so that's why I have put it in here. What it says is the boiling point of chlorine is much higher than that of argon. It asks you to explain fully in terms of structure and the type of van der Waals forces present why the boiling point of chlorine is higher than that of argon. Now, I'm not sure if I'd mentioned this before. Van der Waals forces is a general word which refers to all intermolecular forces. Now, the only type we've learned about so far is London dispersion forces, but we'll learn about a couple more types in the next topic. So we've got to explain fully why the boiling point of chlorine is higher than that of argon, and this is a 3-mark explain question. Now, these come up a lot, and I think you can give quite a formulaic response to this question, and we'll do plenty of practice because this is a good way of picking up marks in the exam. So if I'm answering this type of explain fully bonding and structure question, where it's about melting points, what I want to do is talk about the structure of the substances involved. So that's whether they're covalent molecular, covalent network. If they're covalent molecular, you might want to talk about the actual what the formula of the molecule is. That would be really important. If it's a diatomic, or if it indeed is something like a noble gas, you would want to say that that's monatomic. So you're going to talk about the structure. You're then going to name the van der Waals forces or intermolecular forces involved. You almost always in this type of 3-mark question get a mark for giving the name of the specific type of van der Waals or intermolecular force. Now obviously we only know one at the moment, it's London dispersion forces. And then you get another mark for explaining the link between the type of intermolecular forces and the properties. So I'll show you how I've done that in this question. So structure, I've said chlorine is a diatomic molecule, whereas argon is monatomic. I don't actually need to capitalise argon there, I'm forever doing that. Okay, and then, so we've talked about structure, then we need to name the van der Waals forces. So I've linked this to the question a little bit. I've said the forces broken when both of these substances boil are London dispersion forces. But if there was a difference, you could then explain the difference. But it's important that you cover all of the substances mentioned in the question. So that's why I've said both of these substances contain London dispersion forces, or the forces broken when they boil are London dispersion forces. You should have picked that up. I think it's page 7 and 8 in the notes on this topic that talk about London dispersion forces, so that's an important one to know about. So we've covered the structure, we've named the forces, then we just have to explain the link between the type of intermolecular forces or the strength of intermolecular forces and the properties that we're asked about in the question. So we're asked about the boiling point. So we're told that chlorine has a higher boiling point, so the London dispersion forces must be stronger in chlorine as it has a higher boiling point. And then I've explained why, and I've said this is because chlorine molecules have more electrons than argon atoms. So your 3 marks here, you get 1 mark just for saying that there are stronger forces between chlorine than argon. So even if you don't get this bit about diatomic versus monatomic, if you just say stronger forces, as long as you don't say anything about covalent bonds, because covalent bonds are not broken when chlorine melts or boils. So if you say something about covalent bonds, you would lose your marks in this question. So you're identifying that there must be stronger forces in chlorine. You're getting a mark for identifying and naming that the van der Waals forces present in both are London dispersion forces here, and then you're getting 1 mark for giving the explanation that chlorine molecules have more electrons than argon atoms, and that's why the London dispersion forces are stronger. Okay, I hope that's helped a little bit if you didn't get any of these questions. If you do have any further questions, if any of this isn't making sense, then please make sure you just send me a little email and get in touch. Thanks for listening.